Okay, so my name is Amar. As you already heard, I'll be talking about mastering PCB assembly, the challenges that we faced when we started working on the PCB assembly. So what I usually do is designing these enclosures for the devices, and I play with these. And as our company's machine whisperer, the next logical step when we started working on the PCB assembly was for me to start working on this pick and place machine. This is what we started with. So this is on left stencil printer, and on the right the pick and place machine. And when we started, it was only like this pick and place machine and reflow oven that was behind it. And we are actually still using a manual stencil printer for applying the solder paste onto the PCBs. So, of course, we had to learn a lot of stuff, and we had a lot of failed attempts, and some of these are, our failures, and some of these are the examples I found on the internet, but this is closer to what we should get when we have a fully assembled PCB. So one of the main things that we learned is the importance of reflow profiling. And this here is a schematic of a reflow oven. And reflow ovens have several zones. These are the preheat zone, the soak zone, reflow zone, and the cooling zone. Each of these have their impact to the soldering quality, the quality of the soldering, and the parameters that we can control here are the speed of the conveyor that moves the device, that moves the PCB with the components, and the temperature of each of these heaters. This is a diagram that you usually see on the end of the datasheet for the components, at least people working on the PCB design. This diagram actually gives us a better picture of what we're dealing with here. So we see that there are different ranges of temperatures, actually of times that the PCB spends on different on specific temperatures, and this is a diagram that we will be actually using to go through all of these stages. So these are usually what people use for reflow process, and this is what we have. So it's a tiny little reflow oven that has like 3 zones. So yeah, the first zone is that preheat zone. We must ensure that we don't cross the speed of 3 degrees of Celsius per second. This can cause issues well, I can just show you. I think that I have pictures here. So yeah, if we have if the speed of raising that temperature in preheat zone is too high, we can have a breakage of components. These are probably just exposed to too much heat, but I didn't have any examples. We actually had one of the PCBs where we had a resistor breaking in half, literally, because there were, issues with the reflow temperatures. We can also have issues with the solder splattering all over the PCB, and this can cause solder balls ending where we don't want them. So the second zone is soak, where the solder paste, the solder reaches the liquid state, and this part isn't really that sensitive, but we still need to ensure that we don't expose the device to too much heat, because this can exhaust the flux and we get results like this. This is called graping, and this is head-in pillow. This is especially problematic when we have BGA components where we can it's really difficult to fix the issue later. And this is one of the most important parts. This is reflow. This is where we raise the temperature to above 235 for the solder paste that we're using. We're using leaded paste. There are lead-free solder paste options which require much higher temperatures. We need to ensure that we have enough heat here to get to this stage, to have good wetting of the components, but we also must ensure that we don't go over the temperatures that are suggested, not suggested, that manufacturer stated as maximum in their data sheets. And yeah, just one thing, when I talk about reflow zone, it starts at like 183 degrees, goes above 235 and ends at 183. For preheat zone, what I forgot to say is it's heating the PCB to 90 degrees, it ends there, and we start the soak at 90 degrees and end it at 150 degrees. And these are just the examples of the BGA component, and for those who didn't have the opportunity to see, these are the solder balls, and we need to ensure that we have a proper solder joint between the PCB pad and the component. And then we have a cooling phase where similar goes as for the preheat phase. We must ensure that the cool down of the PCB is not crossing, it's not above this minimum, this speed of 3 degrees of Celsius per second. And yeah, that's all about the reflow process, but there are things that are done in PCB design that can also have the effect here. So this is what temperature does to a PCB, but this is like some old PCB of some arcade. So yeah, one of these issues is twisting and warping of the PCBs. This can happen due to distribution of copper, and this can cause issues in reflow process as well. It can cause slippage of components when we get to that liquid state of solder. It can also move the well, due to gravity, solder can go where it shouldn't. And yeah, also when you have a warped PCB, larger components are much more difficult to, well, some of parts of these larger components are not in good contact with solder pads, so we don't get a good result in soldering them. PCBs can come from the manufacturer warped, but also since it is being exposed to really high temperatures here, this bowing can happen in reflow process as well. In both cases, the temperatures are the cause of this. So what we can do is to ensure that there is a good balance of copper. So what we see here below, here on bottom, is a proper way of balancing the copper inside the layers. And on the left, we can see actually the same thing, but when also considering the traces. And another potential solution is using copper teething. This is especially applicable for places like around the components where we have a lot of copper pads, like BGA components, and we can also use it to prevent twisting when we have PCB panels. Yeah. So it shouldn't negatively impact signal integrity, and it should be electrically isolated from the rest of the PCB. Yeah. So yeah, the next issue is something that probably makes people think a lot about, you know, life and that. So it's tombstoning. It's called tombstoning. So this is an issue that is caused by, again, by copper, and it happens when one part of the footprint, for example, if we have a passive component like these here, we have two pads, and one of these pads is connected to a larger surface of, or let's say larger volume of copper than the other. In this case, we have much better heat dissipation on one side than the other, and this causes uneven heating of the solder, and we get cooling on one side that on one pad the solder paste, the solder cools quicker, and the surface tension pulls the component like you see on these images here. And yeah, this goes for also not just well, you can have a situation where the pad is connected to a wider trace. You can have a situation where it's connected to a via that's connected to a ground plane, or pad being directly connected to a ground plane. And it doesn't matter in all cases. It's a thing that, well, if you're lucky, a manufacturer will, yeah, the manufacturer of the PCB will suggest changes. Another thing that needs to be considered here, and of course this is something that sometimes you don't have a lot of influence over, but component choice. Having too wide of a range between those size of the components can also cause issues. In this example here, we have these relays here, and this part in general is a cold spot on this project. So it creates a lot of a huge disbalance of when we're heating this PCB, and we need to go to much higher temperatures to get this properly soldered. Another thing that I'm not sure if, yeah, I was wondering if this is the proper slide. So another thing that to consider is also the shape of the component. So when we're working with passive components, we don't necessarily have to use smaller components, but to prevent, for example, tombstoning, we can use a narrower component because having a smaller surface of the component exposed to solder will lower the chances of tombstoning. And yeah, next thing is solder paste, and this is also a factor. So the smaller pads that are being used require smaller grains of solder in solder paste. These finer solder pastes are more difficult to handle, and it's are also more expensive, and yeah, it influences the production costs. Next thing is also the PCB itself. We had PCBs, as I've already mentioned, come warped, but one thing that we know happen, I'm not sure if we ever experienced that, but there's issue of copper distribution on the PCB. We need to make sure that the copper is even in all parts of the PCB. And this is done by, we'll see later, analyzing the cross-section of the PCB. So yeah, as I said, how do we fix these issues? First thing is definitely one of the most important things is having a good reflow profile. This reflow profiling requires us to have probes attached to the PCB. It's best if we have it on these copper pads covered by the component that would be used and taken in several parts of the PCB. And what we get from this is a diagram that follows this temperature, and that should follow that graph that we saw in the beginning. So, another thing that's really important is applying the solder paste with that solder printer. We were having issues with, if you don't put the solder paste properly, it will impact all of the rest of the steps in the production. And here you can see the differences between non-treated stencil and with the electropolished stencil. What electropolishing does is it smooths the surfaces of the stencil, the windows through which the solder paste is pushed through. And of course, the PCB design, the things that I mentioned before. Yeah, I actually forgot to put an image here. Great. It's just that image of the project that we did where we see different component sizes. Okay, and this is that cross section that I mentioned. So we can require the manufacturer to send us something like this to have a better picture of what we're working with when we receive their PCBs. Another important thing is controlling the environment in our manufacturing facility, and yeah, this impacts the solder paste quite a bit, and that preheat speed as well. Special care must be taken to ensure that solder paste is deposited. As I said, some people say that this is the most important step, and here we can see what it should look like, although here we can see some smudges which may cause some issues. Sorry. And also we need to ensure that pick and place process works really good, because this can also impact all of the rest of the process. This can be done on at least on more critical components like BGA and QFN components like we have here. So yeah, this is another thing that we need to consider, is controlling checking that the soldering is done well. We do this with visual inspection, but also there are different ways like X-ray analysis for BGA components to check that we have everything done well. And yeah, that's what I was saying. Here we have some batch that we did on that project. And of course, another important part is cleaning the PCBs. These are usually done with really harsh chemicals, and if possible, we should avoid having to do this. But it's necessary when we have to do corrections on the PCBs, and yeah, we need to do all of these things that I mentioned before to prevent having to do any fixes and well, cleaning after. So yeah, to summarize, take your time to ensure a good temperature profile, make sure that the quality of the PCBs you receive is good, do quality checks in all stages of production, and ensure good solder printing quality, do PCB design with manufacturing in mind, and choose the components that will make the assembly easier. So yeah, that's all. Do you guys have any questions about this? Yeah, please.
Okay, so I'm completely ignorant here. So the numbers you showed, 3 Celsius per second, 6 Celsius, is that what you come up with? Or you just show us general things that comes with the whole
So different manufacturers of solder paste have different alloys in solder paste, and each manufacturer provides a data sheet with this diagram, with these temperatures that are required for their solder paste.
So you enter that as a parameter in the machine?
Actually, no. We have to do these tests. That reflow profiling is exactly that step where we use temperature probes. We put them on different parts of the PCB, and we run the PCB through the reflow, and we see what we get. And we change the speed of the conveyor. We raise or lower the temperatures of different heaters to get the required temperatures, to reach the required temperatures at specific times. Yeah.
So only that you can change? The speed?
Yes, exactly.
The temperature of each?
Yes. It would be great if we had something that does it automatically.
So you have a new soldering tape, you need to change it? New different PCB manufacturing, you change it?
Yes. If we change the alloy, we need to... Actually, we need to do thermal profiling for each individual design. So each PCB design requires even different sides of the PCB behave differently.
And how many you break before you get?
Well, we usually order at least 1 or 2, depending on the size of the batch, above the size of the batch. Yeah, yeah, we try to destroy just to.
From both sides.
Yeah. Because we have there are limits on how many times you can expose PCB to these heats. Each time it deforms a little bit, and we have. So one of the issues that I didn't mention here is having if we are running the PCB, if we're doing both sides of the PCB, so we have components on top side and on the bottom side. We need to do this in 2 cycles. And we had to have a part that we mount the PCB on. So in the beginning, we thought, like, let's use an old PCB for this, and we will be running this. And after, like, I don't know how many times, the PCB got delaminated completely. So we got to see what's yeah, everything inside.
And you got all the fumes.
Yeah, that's also fun.
The healthy part.
Yes, yes.
Then we switched to those silicone stones.
Yeah, yeah.
All the PCBs.
That's actually what's used usually in so these are resin, the material that the PCB is mounted now, that we use now to mount the PCBs on, is resin with parts of stone in it. And this helps us because it doesn't dissipate heat a lot, and we don't get these issues where the heat is, it doesn't act as a heat sink. Yeah.
Okay. I was just wondering,
okay, this one.
yeah, when you put the board into the machine, right, you control the speed and the heat, right?
Yeah.
So what if you were to say board is stationary, you have just one heater, and then you use your thermal probes to cycle the heater on and off and create a closed loop?
Yes, those are, that's exactly how a desktop reflow oven works. And we had that before, we used that before for smaller batches. But when we have a large batch, we can just, you know, put like, I don't know, a bunch of these PCBs that are assembled and checked and everything, and we just, and in desktop reflow oven, we can put like 2. That's the thing.
Okay, so we're already out of the 30 allocated minutes.
Okay, thank you.